Hello everyone, today we're going to look at graphs of derivatives and integrals. So if we have the graph of a function, can we graph its derivative? If we have a graph of a function, can we graph its integral? So that's what we're going to look at today. We're going to keep it very basic though. So given the following graph of f of x, can we graph f prime of x? So remember that the derivative is just the slope. So if I have a line, I can figure out its slope just using the formula for slope that we've been dealing with for quite a while, right? Slope, is the change in y over the change in x. So again, this only works if what we have is a line. But if we look at our picture here, we have straight lines for all of them. So to find the slope, to find the derivative rather, we're just looking for the slope. So from 0 to 1, we have this line here, and we want to look at its change in y over the change in x. So the change in y, how high up it goes from 0 here up to 2 here. So the change in y is 2, and the change in x is from 0 to 1. So the slope from 0 to 1, aka the derivative, is 2. So that's the really nice thing with lines. So the next part we're going to look at is from 0 to 2. So from 0 to 2, the slope of our line is 0. We have a horizontal line. There is no change in y. So we have a 0 over our change in x, which happens to be 1 if we're looking at 1 to 2. So that would be a 0 over 1, which is 0. So f prime of x is 0. The next section we want to look at is 2 to 3. So we've got this section here. And again, it's a straight line, so its derivative is just the slope. So here, our change in y is negative 2. We're starting at 2. We're going down to 0. So that's a change in y of negative 2. Our change in x is 1. So our slope, or our derivative here, is negative 2. Our last section is 3 to 4. Again, that's a horizontal line, so the slope is 0. So writing it out, we have a slope of 2 from 0 to 1, or again, a derivative. From 1 to 2, our derivative is 0. From 2 to 3, our derivative is negative 2. And from 3 to 4, our derivative is 0. So that is what it is algebraically, but we do want to graph it, so we're going to do that next. I'm going to change colors into blue. So here's our original graph. Here's f of x. We want f prime of x. And we've already found the values. From 0 to 1, it's 2. From 1 to 2, it's 0. So we're going to move down here. From 2 to 3, it's negative 2. And from 3 to 4, we're back up at 0. So everywhere our function is increasing, we have a positive slope. Everywhere our function is constant, we have a 0 slope. And everywhere our function is decreasing, we have a negative slope. And again, our slopes correspond to our derivatives since our functions are just straight lines. So the first one hopefully isn't too bad. But now let's go backwards. Let's say we're given the graph of f prime of x, and we want to graph f. So this would be the same thing as, here's our graph its integral, right? If I know f prime and I'm looking for f, that's the integral. So we're going to be dealing with the fact that f of x is the integral of f prime of x. Now we always start at 0 and end at x in this case. So it's really the integral from 0 to x of f prime of x dx. And then we need to add to it our original function, or f naught, also sometimes just referred to as f0. It's the same thing. F naught is our initial point, which is f0. So here we have, given the following graph of f prime of x, graph f of x if a, f of 0 equals 0, and b, f of 0 equals 3. So we're going to start with f of 0 equaling 0. So this is going to be plus 0, so we don't have to worry about it. Okay, so we're just looking for f of x equals the integral from 0 to x of f prime of x dx. And that's going to be what we're going to be using to figure out this function. And again, our f prime of x depends on what part of our graph we're looking at. So if we notice, our graph kind of gets split up at these integer points. It's a different function from 0 to 1 than it is from 1 to 2, than it is from 2 to 3, than it is from 3 to 4. Okay. So we're going to start with 0 to 1. So here our function is 0, so f prime of x is 0. So f of x is the integral from 0 to x of 0 dx, which is 0. And again, we had that plus f of 0, right? That's kind of our c, but we know that that's 0, so we're not adding anything onto it. So our function is just 0. From 1 to 2, we're going to look at the integral from 0 to x of f of x dx. Now from 0 to 1, we know that it's 0. So I'm going to add 0, our original integral from 0 to 1, and then our integral from 1 to x of our function here. Okay, so remember the whole thing is the integral from 0 to x, and from 0 to 1 we know that it's 0. So I'm really looking at the integral from 1 to x of our function from 1 to 2, which is 1. So we're looking at 0 plus the integral of 1 dx from 1 to x. The integral of 1 dx is x, and we're evaluating it from 1 to x. So if I plug in x, I get x. If I plug in 1, I get 1. So my function is x minus 1. Okay, so again, this is only from 1 to 2. So we have x minus 1. When I move on to the integral from 2 to 3, I have a new function for f of x. And I also need to know the integral before that. So again, I'm looking at the integral from 0 to x of my f of x dx. What I'm going to concentrate on is from 2 to x, where x is between 2 and 3. And I need the integral before it. So again, from 0 to 1, it was 0. From 1 to 2, remember the integral is the area under the curve. So I'm just looking for what's that area, and that's a 1 by 1 square. So it's going to be 1 plus the integral from 2 to x. Okay. So again, I have this area, or this integral is the area, and it's a 1 by 1 square, so the area is 1. So 1 plus the integral from 2 to x, where again x is somewhere between 2 and 3. And then we need to figure out what that function is. So hopefully it's clear to everyone that it is a line, and then I need to figure out the equation of that line. So we're going to go back to Math 125, and we're going to use 2 points to figure out the line. So I've got the point 2, 1, so I'm going to write that up here. And I've got the point 3, 2. So the first thing I want to do is find the slope. So again, that's the change in y over the change in x. So the change in y is 2 minus 1 is 1. The change in x is 3 minus 2, which is also 1. So the slope is 1. I also need to know its y-intercept. Right? I want it to be y equals mx plus b. So that's the form that I'm going to get for my equation. That's going to go inside my integral. That's what I'm looking for. So what I'm going to do is I'm just going to plug in a point and solve for b. So I'm going to use my 2, 1. Okay, so y is 1, m is 1, x is 2, and I'm looking for b. So if I solve this, 1 times 2 is 2, bring it over, and I get that b is negative 1. So my equation is x minus 1. So again, m is 1, x is my variable, b is negative 1. So this line is the line y equals x minus 1. So that's what I'm going to integrate. So I've got my 1 plus 1/2 x squared minus x evaluated from 2 to x. So that 1 over here is not part of the evaluated from 2 to x, right? That's its own part. So I plug in x, and I get 1/2 x squared minus x. And then I plug in 2. Plugging in 2, I get 0, so I'd be subtracting 0. So I have 1/2 x squared minus x plus 1. So this is going to be that equation for 2 to 3. 1/2 x squared minus x plus 1. So the last section we have is 3 to 4. So again, f of x is the integral from 0 to x of f of x dx. The area, remember again, the integral is the area under the curve. So from 0 to 1, it's 0. From 1 to 2, again, it's 1. The area from 2 to 3, I can do a couple of ways. I can integrate this guy from 2 to 3. Right, that was the integral, so I can just evaluate it from 2 to 3. Or, again, I can use geometry. This is a trapezoid. And I know the area of a trapezoid is 1/2 base times height 1 plus height 2, since our trapezoid is kind of on its side. So I'm going to use interchange my base and my heights. Excuse me. So my base is 1. My height 1 is 1, this guy here. My second height is 2. So I've got 3/2. Okay, so my area from 1 to 2 is 1. My area from 2 to 3 is 3/2. And then between 3 and 4, it's going to be the integral from 3 to x of my function, which is the straight line y equals 2. So I'm going to clean that up. I've got 5/2 from here. And then I've got my integral of 2, which is 2x from 3 to x. And again, that 5/2 is not part of that evaluated from 3 to x part. So I've got my 5/2 plus 2x minus, plug in 3, is 6. So that's going to give me 2x minus 7 over 2 as my equation for my function from 3 to 4. Okay, so it takes a little bit more work finding the integral than it is finding the derivative, but you just got to be careful. And don't forget to make sure that you're adding up the previous integrals, right? You always got to go from 0 to x. So we have these guys. We got to make sure that our picture makes sense. So I'm going to check that our boundary points are equal. So I'll show you what I mean by that. So here are our functions that we had before. So I'm going to look at each of these values here and make sure that from function to function they're the same. It's also going to help me in my graphing. So f of 0 is 0. And according to my first part here, f of 1 is also 0. When I move down to my 1 to 2, I'm going to plug in 1 and 2. When I plug in 1, I better get 0. So if I plug in 1 for x, I do get 0. And I get 1 minus 1, which is 0, so that's good. I need these two guys to be the same from function to function. Now I'm going to plug in 2, and 2 minus 1 is 1. So now when I go down to my next one, when I plug in 2, I better get 1. So 1/2 times 2 squared minus 2 plus 1. It is 1, so that's good. They're matching up. And then I plug in 3. So f of 3 I get 2.5. Now again, when I plug in 3 down here, I better also get 2.5. And I do. If I plug in 3, I've got 6 minus 3.5, and that is 2.5. So again, they're matching up, so it's good. And then lastly, I'll plug in 4, and I get 4.5. So I'm going to plot those points first, and then I'm going to see how to connect them. So for 0 to 1, 1 to 2, and 3 to 4, they're just straight lines. So as soon as I have those endpoints plugged in, I'm just going to connect them with a straight line. However, we have to be careful because from 2 to 3, we have a quadratic. So in order to draw our quadratic nicely, we need to find out where the vertex is. So I'm going to do that next. Okay, so we have our graph, our function, 1/2 x squared minus x plus 1. Again, I'm going to look for the vertex. So if we go back to previous math classes, the x value of a vertex of a parabola that's in ax squared plus bx plus c form. The vertex is negative b over 2a. So my b is -1, so -1 is 1. And 2a, a is 1/2, so 2a is 1. Excuse me. So the x value is 1. The y value is plug in 1. And we get 1/2. So when we graph this, we're not going to put this point in, because remember this graph, this function is only from 2 to 3. So this vertex isn't going to be part of it, because that vertex isn't inside 2 to 3. But we're going to think about that's where it would be when we graph it. So let's see how we put this all together. So I'm going to plug in those points that we found. So we had 0, 0. We had 1, 0. Excuse me. We had 2, 1. I'm going to graph this as best I can. We had 3, 2.5. And then 4, 4.5. Roughly right around there. So again, from 0 to 1, it was a straight line. From 1 to 2, it was a straight line. And from 3 to 4, it was a straight line. So the only thing that we have to worry about is from 2 to 3. So when I go to graph it, I'm going to imagine that vertex, which remember was at 1, 1/2. So I can imagine, I'm going to put this in a different color for right now, that I had a vertex here, and that I would graph my parabola like that. So what I'm going to do is I'm going to go over that with blue, just this part here, and then erase the green part. Okay. So it just make sure it's not looking like a straight line. I do have a curve there. It is part of a parabola. And that's basically all we would have to do. Okay, so this was part A. So let me go back to blue. This was part A, where our function started at 0, 0. Part B said that f of 0 was 3. So the only difference here is that we're going to take our picture here and move it up 3 units. So instead of starting at 0, we're going to start at 3. But the actual picture is going to look the same. So from 0 to 1, instead of it being 0, it's going to be 3. And instead of 2, 1, we're going to have 2, 4. We're going to add 3 to it. And that was a straight line. And then 3 was at 2.5, so we add 3 to it, and it's now at 5.5. It's going to have that same parabola type curve. And then 4, 4.5 is going to go up 3 to 4, 7.5. And again, those are connected by a straight line. So if we have different starting points, all that's going to do is move our graph up or down. So again, A was starting at f of 0 equals 0, and now B is starting at f of 0 equals 3. So I don't have to go back and redo the entire thing. all I'm doing is changing that constant. I'm adding 3 to it. Okay, so don't reinvent the wheel. We already had everything that we needed. We're just, again, moving it upwards. For the next example, we have a position function, which we call s of t, and it wants us to graph the velocity function and the acceleration function. And then it's specifying that the graph from 0 to 2 is 2t squared. So this parabola here is 2t squared, and we're going to need to know that in order to continue on. The rest of it, from 2 to 6, are just straight lines. So when I'm looking for the velocity, remember the velocity is the derivative of position. So when I'm looking for the velocity, I'm just looking for the slope of those guys. So I don't need to know the exact formula, I just need to look for the slope. So we'll start from 0 to 2. So again, we know that it's 2t squared, so I just need to differentiate that, and that's just the power rule. So 2t squared becomes 4t. So the velocity, which again is s prime of t, is just 4t. From 2 to 3, again, we're just looking for the derivative, so we're looking for the slope. So we're looking for the change in y over the change in x. So the change in y, we start at 8 and we end at 4. So the change in y is -4, sorry. And then the change in x is 2 to 3, so that's a change of 1. So the slope is -4 over 1, which is -4. From 3 to 4, we have a horizontal line, and the derivative of a horizontal line is 0. So that one's fairly easy. And then from 4 to 6, again, we have a line. It's increasing, so I know it's going to be positive. It has a vertical change, a change in y from 4 to 8. So that's a change in 4. Horizontal change, the x changing, is from 4 to 6, so that's a change of 2. 4 divided by 2 is 2. So v of t equals 2. So again, finding the derivatives are usually much, much nicer, especially if they're just line segments. So from 0 to 2, we have that quadratic, so its derivative is itself a line 4t. And then from 2 to 3, we have our decreasing line, so its derivative is negative, and it's a -4. From 3 to 4, it's a horizontal line, so the derivative is 0. And then from 4 to 6, it's an increasing line, and its derivative, its slope is 2. So when we go to graph it, we're going to have the line 2t from 0 to 2. So from 0 to 2, the line, 4t. So s prime of t, which again is v of t, is 4t. So we start at 0, 0. We end at plugging in 2. So that's 2 times 4 is 8. So we're going to end at 2, 8. So that's why I have my line there. And from 0, 0 to 2, 8. And then from 2 to 3, our velocity is -4. So from 2 to 3, it's -4, and I'll connect that with a vertical line there. From 3 to 4, it's 0. Again, I'll connect it with a vertical line. And then from 4 to 6, it's 2. So I'll go up to 2 and over. So here is our velocity function. Then the next step, part B, is to find the acceleration. So we're going to need this velocity graph in order to do the acceleration. So remember, the acceleration is the derivative of velocity. So here's our velocity function again. And if I want to find its acceleration, again, all I have are straight lines. So the acceleration is the derivative, which is the slope. So for 0 to 2, we're starting at 0, 0. We're ending at 2, 8. So that is a vertical change, or a change in y, of 8, and a horizontal change of 2. I'm also just differentiating 4t, right? So its derivative is 4. So for this, we actually found the values, so I don't even have to go about doing it graphically. I can do it algebraically, because we did actually find these v of t functions. So So from 2 to 3, my velocity function was -4. So the derivative of -4 is 0 because it's just a constant. From 3 to 4, my velocity function was 0, and the derivative of 0 is also 0. And then lastly, 4 to 6, my velocity function we found was 2. It's still a constant, so the derivative is still 0. And again, we can confirm these by looking at the fact that each of these guys are horizontal lines, and the derivative of a horizontal line is 0. So when I go to graph this function, it's not terribly interesting. From 0 to 2, it's 4, and after that, it's 0. So we have this very lovely box-looking graph here. And that's all we have to do, again, when it's the derivative. So here's another velocity, acceleration, position problem. So given the following graph of velocity, graph A, acceleration, and B, position, given that S of 0 equals 2. So we'll start with A, acceleration. So again, the acceleration is the derivative of velocity. So this is going to be the nicer one, the easier one to do. We're going to break it down to between 0 and 1. We have that horizontal line, and again, the slope of a horizontal line is 0. So A of t is 0. From 1 to 3, we've got this nice increasing line. So again, the derivative is the slope. We're starting at 1, 2. We're ending at 3, 4. So that is a vertical change in 2, going from 2 to 4. And it's a horizontal change of also 2. So I'm getting that the acceleration is 1. Lastly, we've got 3 to 4. It's another horizontal line, so its derivative is again 0. So again, when we graph it, it's not going to be terribly interesting. So when I go to graph it, from 0 to 1, the acceleration is 0. From 1 to 3, it's 1. And from 3 to 4, it's back down to 0. So that is the acceleration, or the derivative. Next up is position, which is the integral of our original graph, which was velocity. So again, we have our velocity function, and we want to find position, so we are integrating. So just like with the acceleration, we're going to break it down from 0 to 1, 1 to 3, 3 to 4. So from 0 to 1, we're looking for the integral from 0 to t of our function, which is 2, so 2 dt. We also need to add to it our original position, and from the original equation, that was 2. So S of 0 equals 2, so I'm going to be adding 2 to this guy. So the integral of 2 dt is 2t. We're going to evaluate that from 0 to t, and then add in our 2. So plugging in t, I have 2t. Plugging in 0, I have 0, and then plus 2. So our first position function is 2t plus 2. From 1 to 3, we're going to have our integral from 0 to t of our whole thing, which again we're going to break down because our integral from 0 to 1 is this lovely rectangle. So we've got a height of 2, a distance or a length or the other direction of 1. So this area is 2. So we're going to add to that the integral from 1 to t of this function, which I'll get to in 1 second. We're going to have that there. And then we're also going to be still adding on that S of 0. So I've got a 2 from the area from 0 to 1, and then I've got my S of 0, 2 over here. So we need to figure out this equation here, and just like before, we're just going to use the fact that we have 2 points on a line. So our first point is 1, 2. Our second point is 3, 4. So the slope is the change in y's over the change in x's. The change in y is 2. The change in x is also 2. So the slope is 1. And then I'm going to use my point here to find b. So y equals mx plus b. So again, that's just the slope-intercept form of the line. So y equals, or 2 equals 1 times 1 plus b. So b equals 1. So our equation is 1, our slope, 1x plus 1, except we have t's. So it's going to be 1t plus 1. So this line is t plus 1. So I'm going to add my 2 and 2 and get 4, plus my integral, 1/2 t squared plus t from 1 to t. I plug in t, and I get my 1/2 t squared plus t. I plug in a 1, and I get 1.5, or 3/2, so I'm going to be subtracting that, so 3 over 2, plus my 4. So I'm going to combine those together, so 1/2 t squared plus t plus 4 minus 3/2. And that's going to give me 1/2 t squared plus t plus 5/2. So that's going to be my equation for my acceleration. And then I have to do 3 to 4. So again, I'm going to have the integral from 0 to 4, but I know the integral from 0 to 1 is 2. The integral from 1 to 3 is again a trapezoid. So to find it, I can either evaluate this guy from 1 to 3, right, because that was the integral, or I can use the fact that it's a trapezoid. And again, it's 1/2 the base, which is 2, from 3 to 1 is 2, times the sum of our sides, which is 2 and 4. So 2 plus 4 is 6. These guys cancel. So I've got a 6 here. So when I go to do the integral from 0 to 4, 0 to 1, 1 to 3, and then 3 to t, really, with t being in 3 to 4. So the function from 3 to 4 is 0. And then again, I have my s of 0, 2 also. And these are where they're coming from. The integral of 0 is just 0, so that goes away. So I just have 2 plus 6 plus 2, which is 10. So s of t from 3 to 4 is 10. Just like the last time where I did the integral, we want to make sure that our points match up. So I'm going to find 0 to 3 and then also 3 to 4 and make sure that between them they're the same. So plugging in s of 0, I have 0 plus 2, which is 2, which is what we want because that's what we were given. And then I plug in 1. So 1 times 2 plus 2 gives me 4. So when I plug 1 into my second set, I better also get 4. So 1/2 times 1 squared plus 1 plus 5/2, that does give me 4. So I do have s of 1 is 4. And then I'm going to plug in 3. So 1/2 times 9 plus 3 plus 5/2 will give me 10. And then when I plug in 3 and 4 here, it's just a constant 10, so it's 10 for each of them. But on my endpoints, they are matching, so that's good. That means I did it correctly. Also, like before, we do have a quadratic part. So again, in order for our graph to make sure it makes sense, we want to figure out where that vertex is. So again, here's our parabola, which goes from 1 to 3. So the t value, in this case, of our vertex is still negative b over 2a. So again, that's going to be negative 1 over 1. So b is 1, a is 1/2, so I get negative 1. I plug that in to find the in this case, s value of our vertex. And we get 1/2 minus 1 plus 5/2, which gives us 2. So again, when I graph it, I'm going to visualize the vertex being at -1, 2. So the first thing I'm going to do is plot those points that we have. So 0, 2, 1, 4, 3, 10, and then 4, 10. So from 0 to 1 and 3 to 4, they were both just straight lines. So again, that quadratic is only between 1 and 3. Again, I'm going to draw it in green at first. So again, we're going to have an invisible -1, 2 being our vertex. So that's going to be kind of off the page a little bit around over here, and I accidentally just got rid of my line. Whoops. Put that in blue. So again, our vertex is somewhere over there. And then just visualize graphing it between those points. And then I'm going to erase the green outside of my 1 to 3. And then just go over it with my my blue so that it makes more sense. So again, just make sure that I can tell it's not a straight line, and then see the work of how you're graphing the fact that it's a quadratic. And that is the position function. Example 5. Given the following graph of the voltage, find the graph of the current if there's a capacitor of 1 farad. So we're going to recall that the current is the capacitance times the derivative of the voltage. So here's our graph of the voltage. So if I want to find the graph of the current, I'm going to take C, the capacitance, which is 1 in this case, and multiply it by the derivative. So the nice thing about C being 1 is I can kind of just ignore it, and I'm just looking for the derivative of this function. So I'm going to split it up into our different segments. So from 0 to 2, we have a straight line, and notice that they're all straight lines, so this is going to be really nice. Again, the derivative is just the slope. So I have the fact that I've got starting at 0, 2 and ending at 2, 4. This has a rise of 2 and a run of 2. So the slope, which is the derivative, is 2 over 2, which is just 1. So I of t is 1 from 0 to 2. From 2 to 3, I have a horizontal line. And remember, the derivative of a horizontal line is 0. So I of t is 0 times 1, which is 0. From 3 to 5, we have a different horizontal line, but it's still a horizontal line. So the slope, or the derivative, is still 0. And then the last section, 5 to 6, again, it's a straight line, so the derivative is just the slope. And it has a rise of 2, and it has a run of 1. So the slope, aka the derivative, is 2. So then we just have to graph it, and it's not too bad. We've got a couple of horizontal lines that we're going to be graphing. So from 0 to 2, we have a slope of 1. And then from 2 to 3 and 3 to 5, we have a slope of 0. So from 2 to 5, the slope, or again, the derivative is 0. And then from 5 to 6, the derivative was 2. So we have a graph that looks just like that. For our last example, given the following graph of the current, find the graph of the voltage if there's a capacitor of 2 farads and an initial voltage of 2 volts. So again, we're going to use that the voltage is 1 over c times the integral of I of t dt plus the initial voltage. So here's the graph of our current. So in order to do the voltage, again, we're going to break it up into the different segments. So from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So from 0 to 1, our function is the horizontal line 1. So we're going to plug it into this formula here. So c is 1. So we have 1 over 2 times the integral from 0 to t I of t is 1, so integral of 1 dt, plus v naught, which is also 2. Okay, so this 2 is my 1/2, this 2 is my plus 2. So when I integrate 1 dt, I have t from 0 to t, which is just going to be t. So 1/2 t plus my 2, and that's going to be my equation from 0 to 1. From 1 to 2, my equation is 3. So I have 1/2 times, now remember this is going to be the integral from 0 to t, where t is between 1 and 2, but I know what it looks like from 0 to 1. This is a square, even though it doesn't really look like it, and the area is 1. So from 0 to 1, my integral, or my area, is 1. And I'm going to add to it the integral from 1 to t of I of t, which is now 3 dt. So that whole thing gets multiplied by my 1 over c, and then I'm still adding my 2. So then I'm going to integrate. I'm also going to distribute my 1/2 here, so I'll have 1/2 plus the integral of 3 over 2 dt is 3 over 2 t, and this guy is evaluated from 1 to t, plus my 2. So when I evaluate from 1 to t, I'm going to have my 3 over 2 t minus 3 over 2, and then I still have my 1/2 on the left and my 2 on the right. So we're going to clean that up. 1/2 minus 3/2 is -1, plus 2 is 1. So I'm going to have my 3/2 t plus 1. So that's going to be my equation for 1 to 2. And then I'm going to keep going. So from 2 to 3, again, I'm going to use this formula. We're going to go from 0 to t. But from 0 to 2, I know what that area is. And again, I can break it down into 2 rectangles. So I have a 1 by 1 rectangle, or again a square. My other rectangle has a height of 3 and a width of 1, so it has an area of 3. So from 0 to 2, I have an area of 4. And then I'm going to add to it my integral, starting at 2, ending at t, of my function, which is 2 dt. And then that whole thing gets multiplied again by my 1/2, and I'm going to add the 2 at the end. Okay, so I have, and I'm going to distribute my 1/2 as I do it, so 1/2 times 4 is 2, plus 1/2 times 2 is 1, so I'm integrating 1, which is just t, and that's going from t to 2, or from 2 to t rather, plus my v naught of 2. The t evaluated from t to 2 will be t minus 2. So when I combine that with my other 2's, one of the 2's cancels, and I'm ending up with t plus 2. So from 2 to 3, my equation is t plus 2. And then I've got 3 to 4. So again, I'm going to go from 0 to t, but from 1 to 1, 0 to 1 rather, it's 2. From 1 to 2, it's 3. From 2 to 3, I have a rectangle of area 2. So again, it's a height of 2 and it's a width of 1. So from 0 to 3, my integral is just 6. So I'm going to have 1/2 times 6 plus the integral from 3 to t of 0 dt plus 2. The integral from 0 dt, the integral of 0 dt from 3 to t is just 0, so that whole thing goes away. So I am left with 1/2 times 6, which is 3, plus 2 gives me 5. So from 3 to 4, my integral, or my voltage, is just the equation v of t equals 5. Right, so remember, if the derivative is 0 rather, then my function is a constant. So I just have 5. So again, in order to graph this, we want to make sure that our endpoints of these intervals match. So I don't have any quadratics here to worry about, so that's really nice. I'm just going to be connecting my points with straight lines, which is always really easy to do. So again, I'm going to plug in my endpoints and make sure they match. So v of 0, I plug in 0, and I get 2, which is good because I was told the initial voltage was 2, so v of 0 better be 2. And then I'm going to plug in 1. So 1/2 plus 2 is 2.5. Down here, I'm going to plug in 1 and make sure that I'm still getting 2.5, which I am. 3/2 plus 1 is 2.5. And then I'm going to plug in 2. So 3/2 times 2 is 3, plus 1 gives me 4. When I plug in 2 down here, I'm also getting 4, 2 plus 2, so that's good. And then I'm going to plug in 3. 3 plus 2 is 5, which is great because I know everywhere from 3 to 4 is also 5. So v of 3 is 5, v of 4 is 5. So again, I'm going to plot those points, so v of 0, v of 1, v of 2, v of 3, and v of 4. And then we're just going to connect them all with straight lines because that's what these guys all are. So I've got my points, 0, 2, 1, 2.5, 2, 4, 3, 5, and 4, 5. And then again, they're each getting connected with a straight line. So notice those lines, it's not one complete straight line. Each consecutive pair of points is connected by a straight line. So if I'm looking at, for instance, this area here, that's not a straight line between all 3 points. Right? This is a straight line, and then this is another straight line. So just make sure that I can tell that they're different lines and I'm not trying to connect it with the same straight line. Okay, so just make sure you've watched this thoroughly. If you have to go back and rewatch it and pause it, that's perfectly fine. But let me know if you have any questions. Thanks.